The other oscillator is also interesting to see, maybe, because you see that sort of gives a sine wave, and it's not that it sort of morphs between a sine wave and a sawtooth wave or crossfades. It's really actually it's a kind of linear FM that I'm using, and I can explain a bit how it works. It's if you do linear FM, you mostly do it with two sine wave oscillators, like the Yamaha DX kind of thing. Now, if you have two of these sine wave oscillators, and like Yamaha, we call them the carrier and the modulator. So you're listening to the carrier, and you use the modulator to modulate the carrier. Now, if they're tuned to the same pitch, and you open the modulation amount, you will hear that the sine wave from the carrier changes to a waveform with the spectrum of a sawtooth oscillator. So basically, you will create all harmonics. If you tune the modulator one octave higher, then you will hear a harmonic series that goes through all the odd harmonics. If you make it 3 times higher, then you would get the 4th, the 7th, the 10th, the 13th, the 16th harmonic. So you would skip 2 harmonics before you go to the next one. So that is basically a way how you can sort of produce this. Well, there's a couple of interesting little things with this, because if you actually have because the thing is, if you really have to tune these oscillators very tight together, which you can only do in a digital way. And they also have to start at the same moment. They have to have a very fixed phase relationship. Else you get actually very different results. So if you want to do this with only one oscillator, you can do it through self-modulation, when you basically feed back its own output to its linear FM input. But if you do this with a sine wave oscillator, you don't end up with a sawtooth spectre, but you end up with a severely detuned result. And that is because if you actually use the sine wave to modulate itself, then you introduce a DC offset. Because there actually also exists something that's called the 0th harmonic, which is basically a fixed voltage level or a fixed signal level. And if this fixed signal level is not 0, it will detune your feedback system. And if you feedback the sine, then you introduce actually also the 0th harmonic, so an offset level, and the thing detunes and it doesn't work. But if instead you also have the cosine available, and you feedback the cosine, and while you listen to the sine, you don't get this DC offset, so you actually get you stay at the same pitch. And then you get the effect that the sine wave sort of like tilts towards a sawtooth kind of waveform. Now, this is easy, because this is just plain feedback. But then if you want to do the odd harmonics, you actually need a sine wave or cosine wave that is twice the pitch of the oscillator. So you cannot directly use this feedback, but you can process the feedback through functions they call Chebyshev functions. And a Chebyshev function will actually change a sine wave of amplitude 1 into a sine wave twice the pitch with amplitude 1. And the way it does that is very simple. If I can find my writing thing. Because let's say that you have a sine wave. And this is 1, and this is -1, and this of course is 0. Now, if you multiply the sine wave with itself, then if you do 0 times 0, the result is 0. 1 times 1, the result is 1. 0 times 0, the result is 0. But -1 times -1 becomes +1. And 0 is 0 again. So actually the result would be a waveform that is a sinusoid of twice the amplitude, of twice the frequency, half the amplitude, and it is positive only. Now, if we multiply this also with the value 2, then half the amplitude becomes full amplitude, and we subtract 1, then we actually get a waveform again between -1 and +1, but with twice the pitch. Now, Chebyshev figured out all the formulas that you need to get the second harmonic, the third harmonic, the fourth harmonic, the fifth. So if you want the third harmonic, you have to do to the third and to the fourth, etc., etc. So basically, if you apply this function in the feedback on this thing, you would actually produce a harmonic series of all the odd harmonics. Then there is another thing, and that is that if you use linear FM, then the modulation index is basically dependent of the pitch of the modulating oscillator. Because
can you say that again?
Yeah.
Not the whole thing, just that.
If you, I just give an example. Let's say we have a waveform at let's say 300 hertz. Now, frequency modulation means that you are going to sweep this frequency up and down. Linear frequency modulation means that, let's say, you sweep it up and down in a way that it goes between 200 and 400. That means that the amplitude of the modulation wave has a certain value that will just produce this. But now if you go to like 600, if you use the same modulation depth, it would actually go between 500 and 700. But the difference between 2 and 400, which is 1 octave, is much more than the difference between 500 and 700, which is much less than 1 octave. That means that the effect here is much less than when you do it here. Actually, you would have to increase the modulation depth by 2 for this 1 octave jump. So you have to keep the same waveform, you actually have to also introduce a modulation index correction, which is also a very simple little formula. And and if you sort of add this all together, then basically you get this oscillator. So if you would sort of look at how you would describe the algorithm in a sort of a basic format, the way I sort of thought it out is that you basically have a sine-cosine oscillator with a linear FM input. So this is the input, you have an output here, and you have an output here. Basically, the simplest way to sort of implement this as an algorithm would be to have a crossfade mixer that crossfades between the sine and the cosine, and you would have this Chebyshev function of the order 1. Then you would do this again, and you have the Chebyshev function of the order 2, etc., etc., etc. Then you mix these all together. There. And then the output goes into the modulation index correction, ME correction, and the output of that one would go back here, and you can have a main switch which would be sort of brightness, but basically by defining the levels of all these, you can basically shape any spectrum that you want without detuning and the waveform being constant over a very wide frequency range.
So when you say there is, like to make the sawtooth, you need all the overtones, but I think is there not something like a limitation of how many of these, say, chips or how many of these procedures you do in parallel before you say we don't need any more to make, like, to approximate the result?
I only use these two in this oscillator because that will already give you most of what you want. I did experiments with more, and to tell you the truth, they don't really add that much more compared to the extra costs that you would have to make to build it. There's only one but. This works fantastic in the analog domain, as you have heard. But if you do it in the digital domain, if you look at these Chebyshev polynomials, because they raise to the power of 2, 3, 4, 5, 6, you very quickly get really large numbers, while you're still trying to be in a range between +1 and -1. So that is a bit tricky to implement properly in the digital domain, although you could use table lookup methods to overcome that. But the nice thing is, because these are all in parallel, because this is basically parallel processing, you can just add the results together, and that actually gives the more interesting things, like that when you PWM kind of things. It breathes a bit of life into the thing. And yeah, this is what I call the canonical form of the algorithm, and yeah, it's not really that difficult to implement. There is a couple of things, you know, how far do you go? Well, the problem with digital calculations is that as we are generating harmonics, partials at higher frequencies, digital systems have a limited bandwidth. And you have to stay within what they call the Nyquist frequency range. So let's say if our sample rate is like 44.1 kilohertz, and you do this with a fundamental pitch of 10 kilohertz, you very soon get into trouble, because everything will reflect back and produce havoc. So it is either you have to use a very high sample rate, and when I did these experiments in the late 80s, where I actually calculated these waveforms from a computer program, first of all, I did the feedback recursively, so I just did it within one sample. I let it feedback many times, and also I used a sort of a virtual sample rate of, if I remember correctly, of 4 megahertz, and then later downsampled everything to the 44.1 kilohertz of the Akai sampler, And so that was always also why it would calculate overnight over just a second of sound. So if you would like to implement this on a laptop or something, you would have to sort of keep in mind that you get these problems, and so you would actually have to use a very high, so maybe within one actual sample, you would do this calculation maybe 16 times, so you would get a virtual sample rate 16 times higher than your actual sample rate or something. But that also takes processing power, which eats away voices. And now I don't care, but I know that many synthesizer manufacturers are really scared about eating away voices, because they rather make a 256 voice really shitty sounding synthesizer instead of an 8 voice really good sounding synthesizer. I don't know why that is, but so yeah, you would have to take into your mind all these kind of things if you would like to do a digital implementation of this. But the analog implementation, it doesn't have all these problems, and because the bandwidth of analog is like 10 megahertz or something, and then higher than 10 megahertz would just be attenuated and not sort of reflect back with weird aliasing frequencies into your audio range. And because the feedback is immediate, and because parallel processing is one of the nice features of you just have, your mixing desk is parallel processing. If you have 8 faders that you can open all the time, it's not that your recording scans through all the faders. No, it's all at once. So I was really thankful actually to sort of discover this algorithm, that it really worked that way in the analog domain, this way. I was hoping somebody would ask me before the lunch break, Rob, how does it work, that oscillator? So, no idea.
The model you drew before, is it a model of FM synthesis or not? Or is it, you say it's linear FM, but not FM as we know it in like a DX model or a John Chowning FM modulation?
That's yeah.
You've got the operator and the carrier, haven't you?
Yeah, well, the thing is, FM means frequency modulation. So that is a very general thing. And you can modulate frequency in many different ways. And one of them is in a linear way. Another one is in an exponential way. And so if you use this linear way of modulating, you're basically doing the same as the Yamaha synthesizers. But in the Yamaha synthesizers, they actually don't modulate the frequency parameter, they modulate the phase. So they push the phase forwards and backwards, which is a slightly different variation that gives a slightly different result, but is actually preferable in a digital system. So I think that the phase, I don't remember exactly, but I think that actually it was Chowning who came up with the idea to use phase modulation instead, so modulating the phase instead of modulating the linear frequency parameter. But it's more or less the same thing. So, but if you look at a DX7, you see that you can actually use feedback, but this feedback only has like 7 levels, and if you set it to level 7, you get noise, and that is basically because at that moment the modulation depth gets so deep that it produces all sorts of rubbish outside the Nyquist bandwidth that turns it into the noise, instead of actually becoming properly chaotic, like in chaos theory chaotic, where you would have like bifurcations and strange attractors and that kind of shit that it would have if you would have a much higher sampler rate. So they're sort of misusing it to create noise. But theoretically, it's not supposed to create that noise. So it's I don't. Yeah, I don't know. I don't. I've never seen this type of oscillator done by anybody else. I don't know if anybody else ever did it. Well, if they did, I don't know of it. But I've always thought that this was so obvious to do that I thought that some manufacturers already would have implemented it. But, well, they didn't, so I had to. And that's my karma, and now I have to build these suitcases.
Do you have to like patent it in a way? If it's something that you can, do you think about ever painting the algorithm in a way?
Patenting.
Patent, yeah. That's the same.
Yeah, well, if you want to do that, that is a process that takes about 2 years, and you would have to hire a lawyer, specialized lawyer company that is going to check worldwide if it's really a unique ID. And I know that in the Netherlands that costs you between 60 and 75,000 euros. And within that 2 years, if somebody else is able to sort of patent it, the same ID, then you still have to pay your lawyer, but you don't have the patent. So I don't know. I don't really think. I hope that I suppose I would have something that they call prior art on this. And yeah, I just hope that this is now for everyone and not just exclusively for 25 years to some strange commercial company. Yeah, I'm not really. I don't know because but I'm in a strange situation because I just do what I like, and I can just do what I like. I can build what I like, and if people don't like it and don't buy it from me, okay, then I have to do something else. But as long as people like it and I can pay my rent and eat my meal every day, you know, why keep things exclusive? I don't really sort of tell everybody this is how it's done, you know, they can figure it out for themselves.